I want to begin with a statement of the fundamental theorem of calculus.
Suppose the function little f from the closed interval a to b to the real numbers is a continuous function. And let's define the function big F to be the accumulation function, right? That's the integral from a to x of the function little f. Well, then the function big F turns out to be continuous on the closed interval a to b, differentiable on the open interval a to b, and this is the big point, the derivative of big F is little f.
We've seen a bit of evidence for this already.
Suppose I got the accumulation function, so big F of x is the integral from a to x of f of t dt. And now I can ask, how is the accumulation function changing? Well, the accumulation function is increasing, meaning its derivative is positive, if the function that I'm integrating is positive, and the accumulation function is decreasing, meaning the derivative is negative, if the function that I'm integrating is negative. And this suggests that the derivative of the accumulation function and the function that I'm integrating might be related in some way.
Here's a graph that's particularly compelling.
So I'll draw the coordinate plane. Here's the y-axis. Here's the t-axis in this case. And then I'll draw some random looking graph. That'll be the graph y equals f of t. And then I'll pick some point, I'll call it a, and some other point x. And then I'll look at the area under the graph between a and x, right? And that's the integral from a to x of f of t dt, right? That area is the accumulation function evaluated at x.
Now, what's the derivative of the accumulation function?
Well, I've got the accumulation function, right? F of x equals the integral from a to x of f of t dt, and I don't know how that changes when x changes. So let's make a small change in x. Let's go from x to say x plus h, and then ask how does the area in this region compare to the area in this much larger region?
Well, what's big F of x plus h minus big F of x?
Yeah, so what's f of x plus h, right? That's the area from a to x plus h, minus f of x, big F of x, that's the area from a to x, and that difference, right, that difference is just the area inside here.
That little leftover piece is practically a rectangle of height f of x, little f of x, and width h.
I mean, this region is not quite a rectangle, but it's awfully close to a rectangle of width h and area f of x plus h minus f of x.
Remember, my goal was to differentiate the accumulation function.
And all I've got is this rectangle whose width is about h and whose height, if you think about it, it's about f of x. So what's up with this rectangle, right? I mean, what I've really got here is a rectangle, and its area is about f of x plus h minus f of x, this accumulation function. Its width is h, and its height's about f of x. Well, if I've got a rectangle with this area and this width and this height, right, what do I know? I know its height times its width is its area. So if I take its area and divide by its width, I should get its height. Now, all this is just approximate, but let's write that down, right? The area of this rectangle is f of x plus h minus f of x, and if I divide by the width, I should get the height.
What does that mean after I take a limit?
Well, of course, this is only approximately true, but if I take a limit, right, if I take a limit as h approaches 0, this gives me the derivative of the accumulation function, and that will in fact be equal to the function's value.
And that is the whole game.
The accumulation function big F is an antiderivative of little f.
Well, this is really remarkable.
For instance, you might be wondering, what's an antiderivative of this function little f of x equals e to the negative x squared?
Well, if a function's continuous, then we can find an antiderivative. The antiderivative is the accumulation function.
So an antiderivative of e to the negative x squared is the accumulation function. I can define a function big F of x to be the integral from a to x, for some number a, of e to the negative t squared dt, And if I differentiate this accumulation function, I get back e to the negative x squared. So I found an antiderivative for this function.
Well, I can't write it down any more nicely because I can't write down an antiderivative for e to the negative x squared using the functions that I have at hand. But nevertheless, the antiderivative is the accumulation function.